Have you heard about stream function and velocity potential? Anyone? No, right? Okay. Somebody geleng kepala tu. Okay. So this is what we do in chapter number 2. Okay. So the first learning objective is apply the concept of stream function and velocity potential. Okay, number 2 is characterize simple potential flow fields. I mean, the flow is you normally see, but you're gonna give some special name for it. Okay, doublet, rangkaian half body, right? So this kind of thing. So basically, do not get surprised. The only thing is the names and the terms. So that's all it is in this potential flow. Okay, the last one is understand superposition as a method of solving potential flows problem. Superposition is combination of elementary flows. Okay, perhaps we combine one type of flow to the other type of flows, and those combination we call that as a superposition. Okay. All right. Potential flow. Okay, in real life or in actual, the fluid flows with a certain viscosity, for example. Okay, actual flow. Okay, but here when we analyze, we're gonna apply a concept of ideal flow. So what is ideal flow? It's actually a purely hypothetical fluid which lots of assumption. Okay, we assume there's no viscosity. Okay, what it means by no viscosity? Muhammad Izra. Muhammad Izra. Are you there? Okay. Said Ahmad.
Yes, sir.
What it means by no viscosity?
Dia cair macam tu.
Come again? Said. Repeat your answer again. Okay, alright. Kecairan. Okay, set up your microphone. Set Ahmad. Switch on your camera. Okay, so yeah, basically you translate it into Malay. Okay, so no viscosity meaning we're not gonna apply shearing stresses. Okay, in actual, in real, should not be like that, right? Even water also have their own viscosity. Like our previous example before, The viscosity is 1 times 10 to the power of -3. Okay. And those are the other assumptions: incompressible flows, no compressibility, and no surface tension, as well as no vaporization. Okay. Okay. Next, what we do is we categorize the fluid motions. There are two fluid motions. Okay, number one is translation. Number two is rotation. Okay. So ideal flow also, we can characterize it into when the fluid is steady, meaning there is no change in time, and incompressible when the density does not change with pressure, non-viscous, and irrotational. Okay. Non-viscous is no shearing stresses. Irrotational, later I'm going to explain what is irrotational and rotational. I'm going to draw you a figure for you to better understand about those terms. Okay, so these are the fluid motion. Okay, first what we need to have is the initial condition. Okay, and after that, when the fluid moves, so the element will move based on 1, 2, 3, 4, either translation, linear deformation, rotation, or angular deformation. Okay. Muhammad Khairul Ikhwan, is it?
Yeah, yes, sir.
Can you give me, can you try to explain what are the difference between translation and rotation?
Hmm. Tahu, sir.
Take a look at the figure.
I think translation involves some kind of like a full movement, while rotation involves a rotation at an axis or an angle. I think so.
Very good. Okay, correct.
Oh.
Yes. Yeah, that is the explanation of translation and rotation. Thank you, Khairul Ikhwan. Where's your camera? Switch on. Okay. Yeah. When you have a rotation, it should be one of the original position become some sort like a datum. Is it datum? No. Constant. Okay. And it rotates along the constant or axis. Okay. Meanwhile, translation is the whole part of the fluid element is moves to the other side. Okay. Without any rotation at all. Okay. All right. Now tell me, Muhammad Naufal.
Yes, sir.
How about linear deformation and angular deformation?
Linear deformation. Linear maybe deform at only one axis. Angle maybe involves angle.
Okay, the first one, Naufal, is the element will become larger and smaller, right? Can you see?
Yeah.
Yeah. Alright, so that is the first one. And then what are the other thing? The other one. Take a look at the names itself. When it deforms, one deform because of one deform with an angle, another one deform linearly, right? So those are the difference between linear and yes, Adiba. Okay. Difference between linear and angular deformation. Okay. Now, switch on your camera, find camera and set up. Okay, so those are the movement of fluids. Okay, based on what Adiba explained, linear deformation shape remain the same. Angular deformation shape will change. Yeah. The how it looks like is going to be changed, right? Yes, correct. Okay. So next is we talk about no viscous flow. Okay. The other name for it is inviscid flow. Okay. Which are when the shearing stresses assumed negligible are said to be inviscid, non-viscous, or frictionless. All three names basically give us the same information. Okay, only the names are different. Okay, an inviscid flow is the flow of an ideal fluid that is assumed to have no viscosity. All right. Statement number 3. Okay, remember Navier-Stokes equation? Right. So I open up for you. This one can. Right. So I need to use this one. Okay. So this is Navier-Stokes equation. If the flow is non-viscous, which one we cancel out?
Yang ada mu tu.
So meaning for x component, this one is cancelled out, right? Since we assume there is no viscosity, so everything is cancelled out. Okay, so that's what happened to Navier-Stokes equation when we use ideal fluid as our study, right? Or we assume ideal fluid. So there is no viscosity. Yeah, very good. So yang ada mu, everything cancel out. So there is a name for this. Now the Navier-Stokes equation becomes what we call as a Euler equation. Euler equation. This one. Viscous term neglected. Okay, so everything else is remain. The acceleration field, the pressure difference, the gravitational effect, everything's are remain. Okay. All right, any question up until that point?
No question, sir.
So what I explained actually, in our part previously, about what?
About the formula. And the thing that should be cancelled
Because of what?
because of no viscosity.
Lagi sikit lagi. The main part, because we assume no shear stress because of assumption. Because of what? Yeah. Because we assume real fluid now become ideal fluid. So you should remember that. So that is the first part of my lesson today. Okay. Everything else, everything is every fluid flows, we assume ideal fluid. Okay, no viscosity, no shearing stresses, incompressible. What else? No vaporization. Okay, and I introduced to you the what happened to NSE when we assume the fluid. Okay, right. Next we go to the one that I mentioned just now. You haven't encountered before. Okay, so we call this as stream function. Okay, somebody, how we call this one? Can you guess? Please give me some few guesses.
Sky.
You know, right? How did you know?
Google, sir.
Okay. Alright. It's okay. Alright. But this is the first time you encounter this one, right? Yeah. So string function, the symbol we call that as psi. How we pronounce it is SAI, as simple as that. How we spell it is ESI. Yeah, you try. You can Google that. Okay. All right. Stream function exists for if the flow is both irrotational flow or rotational flow. All right. So now is the time for me to explain irrotational flow and rotational flow. So I need to draw some figure. So the fluid is actually rotates. Okay. counterclockwise. Okay, and maybe here I try to draw this element. So this is represent the element on the fluid path line. Okay. Now I go to figure number 2. Same, still rotates counterclockwise. Okay. And all right. Can you see the difference between figure A and figure B? One of them is rotational, another one is irrotational. Okay. Muhammad, is it Muhammad? Najmi Aminuddin. Between
Yes,
A
sir.
and B, which one is rotational? Which one is irrotational?
Uh, B is rotational. A is irrotational.
Okay, so that is the answer from Najmi. Thank you. Nazrin Shah.
B is rotational, sir. A is irrotational.
Okay, that one is from Nazrin. Um, Natasha.
I think A is rotational, B is irrotational.
Okay, that is from Natasha. Thank you, Natasha. Hidayat. Muhammad Hidayat. Hidayat is A rotational, B is irrotational. Okay, so basically 50-50, right? The first two from our friends is different answer, and other two is different answer. Okay, take a look at the element. Okay, the first one that I want you to realize that both are rotates, right? The path line rotates, right? Both are rotates counter clockwise. But in order for us to categorize whether the flow is rotational or irrotational, we're not gonna see or observe the path line. What we're gonna see is what happened to the element in the path line. Okay, the fluid element in the path line. So 1, 2, 3, 4. Is it rotates or not, this element? when it goes along this path line?
No.
Does not rotate, right? How about this one?
It does rotate.
It does rotates. So basically A is irrotational, B is rotational. Okay. So this one is irrotational and this one is rotational. Okay. So I take this opportunity, okay, since I already explained about these terms. So how does we basically analyze rotational and irrotational flow? Okay. We're gonna use this one. Can you guess what is the symbol of that? Dia macam huruf Ain terbalik. Kan? So what is the name of this? Muhammad Irfan. Muhammad Irfan.
Yes, sir.
So what do you think the names for this?
Okay.
It's okay. First time, right?
Yeah.
First time you encounter this one, right? Okay. The symbol, we call this as zeta. Okay, this is zeta. Some spell it Z-H-E-T-A. Okay. Some spell it like this, zeta. Okay. So this is for vorticity. Okay. So this vorticity is the judgment for us whether the flow is rotates or irrotational. Okay. So how we're gonna analyze this one is when zeta is equals to 0, the flow is irrotational. Okay. So zeta is actually this one. Can you see? 1, 2, 3. 3 symbol. All 3 are different. Quite difficult actually to write down this one. Okay. Zeta is actually del V over del X minus del U over del Y. Okay. Right? So when this del V over del X minus del U over del Y equal to 0, meaning the flow is irrotational. But if not, the flow is rotational. Okay. So perhaps later you're gonna have V, for example, V equals to something. Okay, like before, V equals to 4x plus 2y, for example. And then you gonna differentiate that into x, and perhaps you also have U, and if it is equal to 0, the flow is irrotational, or vice versa. Okay. So now we go to another terms. This is when zeta makin teruk jadinya. Okay, zeta is not equals to 0. Okay, when you have zeta is not equal to 0, the flow is rotational. Okay, this is rotational. So we have another name for this. Okay, when the flow is rotational, another symbol. This one. Yeah, that one. Okay. Kappa. Okay, the name for this one is kappa. So how we calculate kappa is zeta dA. So you're gonna integrate towards the area, all right? So kappa is circulation, zeta is vorticity, kappa is circulation, right? So can you see? All of these are basically the one that you normally see in everyday lives. But the thing is, the symbol, this representation of that observation, zeta, kappa, right? So open up your mind, this is how we analyze. Okay, instead of simple rotation that you can see in everyday lives, now it becomes kappa. Now it becomes zeta. Okay, so accept it. Okay, try to grasp all of these things. Later, doublet. Okay, there are another name for that. Okay, all right. So we go back to the stream function. Psi kan, stream function. Okay. So I already explained to you about irrotational flow and rotational flow and all the terms related to that. So stream function applied for fluid having only for 2D flow. Okay. And the equation is come from U and V. Okay, so U equal to del psi over del Y, V equal to negative del psi over del X. All right, so I try to perhaps introduce to you how basically we came up with those equation. So the only thing that you need to remember is this one. But this is just how basically this equation is determined. Okay, so it starts from continuity equation. So you have del U over del X plus del V over del Y plus del W over del Z equals to 0. Okay. So from continuity equation, since our assumption is 2D because we want to derive stream function, so it becomes del U over del X and del V over del Y only. Okay. Okay, let's propose stream function, okay, into the u and v equation. Okay, let's propose that u and v are related by the function. Okay. So we propose this one. U equals to del psi over del y, and then v equals to negative del psi over del x. So what we want is actually whether the flows is this proposal is actually produce or satisfy continuation. So let's check whether it is satisfied or not. Okay. So you're gonna put that into the equation. So del over del x. So u is actually now is del psi over del y plus this is del over del y. So now it becomes negative del psi over del x. Okay. So in the end, what you have is del psi divided by del x del y minus, right? So del psi, sorry, del square divided by del x del y, so equals to 0. Okay, so in the end, the whole term is also 0, so meaning it is satisfy our continuity equation. So our proposal is correct. So based on that, we develop the stream function of the Cartesian coordinates. Okay. So later, if you want to determine the stream function, what you're gonna do is you're gonna integrate towards y, right? So this one is transferred here, become u dy, and then after that integrate to determine the psi. Okay. All right. Now I want to explain. After you realize this one, we go to another one, which is velocity. This one. We not only have in Cartesian coordinates, we also have in cylindrical coordinates. So VR and V theta. So equals to 1 over R del psi over del theta. V theta equals to negative del psi over del R. Okay, so another equations. Okay, next we go to velocity potential. Okay, so for velocity potential, this one we call as phi. Yes, now is psi, now is phi. So phi is for irrotational flow only. Okay. So later you check whether the flow is rotational or irrotational. I gave you the equation how to check that one. Okay. So the equation will be this. For Cartesian and cylindrical coordinates. So u is del phi over del x, v is del phi over del y, w is del phi over del z. Okay, and this is for cylindrical or polar coordinates pr, v theta, and vz. Okay. So what are actually stream function and velocity potential? Okay, Sir already gave the equation how to find the psi and phi, right? So now I'm going to explain to you what is psi and phi actually. Okay, in order for me to explain, I would like you to draw me something. Okay, before this we've learned how to draw the velocity profile, right? When you have a plate fixed at the bottom and you have a plate move at the top and you draw the profile, remember? So like a triangle. This one, the profile, the velocity profile. Okay, now I'm going to give you one example of fluid flows that you see in everyday lives. Okay. Can you see? Boleh nampak eh?
Boleh, sir.
Okay, alright. Okay. We can see this one in everywhere, right? Again. Water. Okay. I mean, pond, for example. Okay. So draw for me the velocity profile, how it looks like. Now, everybody. What do you think the profile looks like? Okay, done? Okay, so now, semua dah? Angguklah kalau dah. Right, okay, now, angkat, tunjuk dekat kamera. I want to see. Show it in your camera. This one is Najmi. Okay. He did it, yeah, but circulate. Okay, that one is Najmi. Okay, next. Everybody. Sekarang, tunjuk sekarang. Janganlah do not wait for your friend. Everybody now. Satu, dua, show it now at your camera. I want to okay. Showing me. Adiba. Show Adiba. Angkat. Everyone. Okay, Adiba, they have three droplets. Okay. Alright. Now one droplets. Okay. But I can see how it looks like. Okay. Who else? Now it's not the time for me to see your face. I want to see your drawing. Shahmi, show me your drawing. Muhammad Shahmi bin Salim. Okay. Okay. Alright. You all too shy. I don't know why. Okay. The phenomena, what we call that phenomena? Water droplets bounce on a pond, right? Okay, the other thing, there's a name for that, special name for that. We call that as source flow. Source flow. Okay. Yeah, the one that you see in everyday life or in real world, water droplets bouncing on a pond. But when we put it in engineering terms, we call that as source flow. Why source? Because we have a position at the center. There is a source here at the center. I thought I shared. Right. Okay.
Yes, sir.
Alright. There is a source here at the center, right? And after that, this one. And this one, it goes larger. Okay. From smaller and after that goes larger and larger and larger. Okay. Alright. So let's take a look again at the water droplets. So again, see, there is a ripple. Okay, it goes from small and become larger. Okay, somebody and that just now somebody draw 1, 2, 3 droplets. Okay, it's okay, but the one that we analyze is only one of them. Okay. So this is how we draw. Okay. Okay. Can you see the direction of flows? Where is the direction of flows? Inward or upward?
Oh, wait.
Upward, right? So from a source, it goes upward, the ripple. So D direction, you draw something like this. This one is actually psi. This is psi, or stream function, which is the direction of flows. Okay. How about the ripple? The one that you observe. That one is actually phi. So we're gonna have three phis. Okay, based on our drawing here, phi number 1, phi number 2, phi number 3. In normal categorization, phi number 1 meaning the first ripple, second ripple, phi number 2, and then third ripple, phi number 3. So these are psi and phi. So now you know what are the difference between psi and phi. Okay. So in order to calculate that, yeah, we're going to use this equation. All right. Okay. Any question? So far, okay? So next, what we do is we can apply a relationship. Okay. What happens when we relate stream function and velocity potential? Okay. The first one is when you relate because of both have u, right? U equal to del psi over del y, u equal to del phi over del x. Okay, meaning this one. So when you relate u equal to del psi over del y, del phi over del x, and v equals to del phi over del y equals to negative del psi over del x, when you do this, there is a name for this. We call this as Cauchy-Riemann equation. By right, it looks simple. I mean, yeah, just we just equate u for both psi and phi, but somebody gave a name for that. We call that as Cauchy-Riemann equation. So let's say during exam, please analyze your problem using Cauchy-Riemann equation. So if you don't know, you thought it's going to be difficult, but no, only that. Okay. Next is Laplace equation. Okay. So for Laplace equation, when you have del squared psi over del x squared plus del squared psi over del y squared equals to 0. So this is Laplace equation for stream function for psi, which is a stream function. So how we determine this one is basically we use zeta equation, right? From zeta, which is del v over del x, okay, remember? And then you have del u over del y equals to 0. So we're gonna replace psi. So del over del x, v is del psi over del y minus del over del y, and then we're gonna put negative del psi over del x, right, equals to 0. So if you solve this one, you will determine this. Okay. So this is actually zeta. Next is Laplace equation for velocity potential, right? So for Laplace equation for velocity potential, okay, you're gonna use continuity del u over del x plus del v over del y equals to 0. Okay, how we derive Laplace equation for velocity potential? We use continuity equation. So you're gonna do the same. You're gonna put this one del phi over del x and del phi over del y. Del over del x, del phi over del x plus del over del y and del phi over del y. This one equals to 0. So in the end, what you have is del squared phi over del x squared plus del squared phi over del y squared equals to 0. So this is the Laplace equation for velocity potential. All right. So any other thing? No, that's it. So that is all about the stream function and velocity potential. Okay, any question? So now if you, you try to see anywhere in your everyday lives when the fluid flows, when it flows, meaning that one is actually stream function. But what happened in between, like the ripple, is actually the velocity potential. Okay. Alright, so next we go to the first example. Okay, Syed Ahmad Fatahuddin. You don't have your microphone? Oh yeah, too bad. Okay, Wan Yusuf.
Yes, sir.
Alright, can you help me out? Read this example.
In a two-dimensional incompressible flow, the fluid velocity component are given by u equal to x minus 4y and v equal to negative y minus 4x, so that the flow satisfy the continuity equation and obtain the expression for the stream function. If the flow is potential, obtain also the expression for the velocity potential.
Alright, terima kasih. Thank you.
Okay.
Okay. So now you have the U and V, the velocity field. Okay. So the first one, you need to show whether the flow is satisfy continuity equation or not. Right? Do it for me now. Okay, does it satisfy continuity equation?
Yes.
Okay,
Yes.
what you get for the first expression? I mean the first term. When you differentiate towards x.
1.
1, right? So this is 1. And then plus
-1.
-1. So equals to 0. So meaning satisfied. Okay, done. So that is number 1. Okay, number 2. Obtain the expression for the stream function. Right. So you have both u and v. Okay. Find psi. So the stream function is right. I show you here. Yeah. In the appendix, the stream function will be given for both Cartesian and cylindrical. So u equal to del psi over del y and v equal to negative del psi over del x. Negative del psi over del x. All right. So what we're gonna do is we're gonna try to solve, use these two equations to determine psi. Okay. So first we solve for u. Okay. So u is x minus 4y. Right. So obviously what we want is actually psi. So you need to integrate towards y. Okay, you now psi become Anyone? Psi equals to?
xy minus 2y squared.
Into 2 now. Okay. So V equals to negative del over del x xy minus two y squared plus c, right? So now is the time for you to put the v. Okay, v is negative y minus 4x. Negative y minus 4x equals to negative del over del x xy minus 2y squared plus c. So what you're gonna have later is this become negative y only. Okay, this term there's no x here, so nothing happened. So become negative del over del x and then c. Okay, you want to find c actually, right? Okay, so next we can cancel out this one, negative y because the same, right? So what gonna happen is you're gonna have negative for x equals to negative del over del x and then c. Okay, so this negative is cancelled out, so you're gonna have for x equals to del over del x c. Okay, so therefore c is equals to yc. We need to integrate this. Maybe I
2x
jump this
squared.
one. Yeah, very good. So for x dx, right, plus, sorry, equals to del c. So when we integrate this one, del c is become c. This one become, apa tadi? 2x squared, is it? Okay, 2x squared. So that this is c. So in the end, your equation is psi equals to xy minus 2y squared plus 2x squared. Okay. So that is the answer for psi. Any question? How about number 3. Okay, we have another one, which is determine the velocity potential. Okay, number 3, velocity potential. Okay, same approach. Okay, since we have U equals to del phi over del x, and then V equals to del phi over. Okay, same approach. Okay, so for one of them, perhaps start with U, and the solution, you put it in the V, the next equation, which is V, you'll find the answer, right? So try to do this on your own. Now, I give you 5 minutes.
sir. Nak tanya boleh sir?
Yes.
Dalam calculation tu kan, kenapa dia tinggal C je sir?
Come again.
Yang apa,
This one.
sub 3 into 1 tu, xy minus 2y square plus c, kenapa tinggal c je?
Sy minus 2y squared plus c. This one
Kenapa
is
bawa?
okay. This one, right?
Yeah.
Okay. Again, your question.
Kenapa kat bawah tu tinggal c je?
Okay, this one is first we differentiate xy, kan? So become negative y, correct?
Yeah.
So negative 2y squared differentiate towards x, tak ada kan? No,
Oh yeah.
right? So in the end you have negative del over del x c.
Okay.
Okay?
Okay.
Am I answering your question?
Yes sir.
Okay, clear, right?
Sir.
So
So in our calculation, we cannot assume C as constant lah, sir, kan?
C as constant. What do you mean?
Because if C is a constant, then if we differentiate C with respect to X, we would get 0 lah, right, sir?
Which one? This one?
Atas dia. Atas lagi. Yang tu.
Okay.
Biasanya kan kalau kita differentiate constant dapat kosong.
Okay, but the thing is, what you want is actually you want to find C. Our objective is to find C, right? So how we do this is we're gonna transfer this dx to the other side. So become what? For x dx, right? And then we integrate both left hand side and right hand side. So this is become 2x squared, and this is become the differentiation of c when we integrate becomes c. Okay? Clear?
Clear.
Now I know what you feel is actually this one, del over del x c, so becomes 0. But if we do like this, everything else becomes 0. Every c becomes 0. Every constant becomes 0. But now no, because we have 4x here, so we can find is the actual c. Okay? Clear?
Clear, sir.
Okay. So what is the phi? Anyone? Phi equals to? What is your answer?
X square over 2
X square over 2
minus 4yx
minus 4y
x
x
minus y square over 2.
minus y square over 2. Okay. How about others? You got the same? Right. Okay. So that's how we determine psi and phi. Okay. So remember, get back to this equation, this problem. The U and V come from actual observation of fluid flows. Okay, meaning you have a fluid flows in U direction and V direction. So what we do from there is actually you determine the stream function and velocity potential. In actual fluid flows, you can see stream function and velocity potential. Now here what you do is you can calculate what is the stream function, what is the velocity potential. Okay, all right. Okay, now we go to example 2.2, but here is also Cartesian, so I'm going to give you the answer for this. You can try this at home. You are at home now, right? You can try this. Wait. Okay. Determine the stream function. Okay, the answer this one would be x squared plus 2y squared. So psi equals to xy plus y squared minus x cubed over 3. So that is the answer for A. And then for B, obtain the expression for component velocity U and V. So U equals to B plus 2CY, and then V is equals to negative 2AX plus BY. You don't like it. B equals to okay, and then verify the flow is satisfy continuity equation or not, and then locate these tension points. Okay, how you locate these tension points is when U equate with 0 and V equate with 0. Alright. I'm not gonna show it here because I'm gonna show it later in this one. Okay, but the concepts are similar. Okay, so those are the answer for example 2.2. And then we go to 2.3. Okay. So this one maybe I erase. Okay, in the meantime, you can fill in your attendance. Okay, we still got 10 minutes. Okay, try to solve this one. All right. You have this kind of flow field, stream function. Psi equals to negative UR sine theta plus Q divided by 2 pi theta. Okay, so at the moment, no need to worry about this term. Sorry, because it looks quite pelik kan. Alright, but the thing is, you will derive this one later in the next subject. Okay, so obtain an expression for the velocity field. Okay, so remember you have polar coordinates and Cartesian coordinates. So since this one involves theta, meaning the velocity field is not going to be u and v. It's going to be vr and v theta. Right? So from psi here, psi equals to negative ur sine theta plus q divided by 2 pi theta. So first we determine VR. Okay, so take a look the equation for VR. 1 over r del psi over del theta, and v theta is negative del psi over del r. So in this one equals to 1 over r del over del theta. So you put back the psi. What is the sign? Negative ur. Negative ur sine theta plus q divided by 2 pi theta. So obviously what you need to do is you integrate this one towards towards theta. So what you're gonna have is sine theta integrates, differentiate towards theta become sine theta, differentiate towards theta. You are cos, right? Cos theta plus q divided by 2 pi. So we simplify this equation become negative u cos theta plus q divided by 2 pi r. So this is VR. Okay. So next we go to v theta. So v theta is negative del psi over del r. Right. So negative del psi over del r. So meaning del over del r, psi is negative ur sine theta plus q divided by 2 pi theta. Okay. So here is differentiate towards r. So there is no r in this term. So we left with negative u sine theta. But here you have negative, right? So negative become positive. Okay. U sine theta. Okay, done. So that is your VR and V theta. Okay. Number 2, determine these stagnation points and show that psi 0 at this point. So basically, when I answer this one, you get the idea how to answer this problem, stagnation points at example 2.2. Okay. So what is stagnation points? Okay, stagnation point is when you have a fluid flows, when it touch a solid body, for example, so it's going to become something like this. You have what we call as a fluid flows over a body, right? Okay, but the thing is this one. Here is stagnation point. Okay. So what are the characteristic of stagnation point is there is no velocity here because it touched the body, right? So meaning V is equals to 0. So for our case, we have component velocity. V is in terms of VR, in terms of V theta. So meaning both are 0. Okay, right? So we're gonna use this one, VR and V theta. Okay, what we want is actually the point. The point meaning the direction points, right? So the direction and the magnitude. Direction is theta, magnitude is dr. So let's start with direction. Okay, so meaning V theta. V theta equals to what? U sine theta just now, right? U sine theta. Okay, so meaning if theta 0 equals to U sine theta, therefore sine theta equals to 0. So meaning what are the angle that produce theta 0? That produce sine theta 0? Anyone? Sine 90 is 1. This is almost you know, right? Sine 90 adalah 1. What does produce sine something theta equals to 0?
0 degree.
0, right? Okay. And we have both 0 and 180 degree, correct? Okay. So we choose one direction only. Yeah. So this is X and this is Y. Okay. But for this chapter number 2, chapter 2, your 0 degree start from this position. This is 0 degree, not here. Quite late, but yes, that's how we do. So here is 0 degree. Can you give me time? I need to check. But I still remember 0 degree start from here. Okay. So I need to check back. But at the moment, tak apa dulu. Kita pakai je 0 degree dahulu. Okay, because both are the same. So now you have the magnitude, which is theta 0 or 180 degree. But we choose this one first. Okay. So next is the time to determine direction. Magnitude R. So we're gonna use VR. So VR equals to negative U cos theta plus Q divided by 2 pi R. Okay, so VR is 0, negative U cos 0 plus Q divided by 2 pi R. Okay, so our objective is this R, right? Want to know what are the magnitudes of R. So negative U cos 0 meaning negative U 1. Cos 0 equals to 1, right? So plus. So plus Q divided by 2 pi R. So determine R. Positive 2 pi U divided by Q terbalikkan. So you have Q divided by 2 pi U. Right? Yes. So that is the magnitude and the direction of R. This problem. Okay, done. So I'm gonna give the answer for the next problem. Okay, determine the stream function for this flow. Psi, number 3. So psi equals to yqx plus, is it 4? I even cannot understand my tulisan. 4 good. Okay. Yeah, you try that. 4qy. 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 So that is psi. Okay, this one you can determine. This is 1, 2, 3 dimension. This one compressible or incompressible, you need to use continuity equation. Check using continuity equation. Okay. So I think that's all for today. Any question? I'm only got 21 respondent. So please, everyone, fill in the attendance now. Okay, while waiting, your friend, any question? Fill in attendance. $23, another 34, another one. Okay, all right. If no question, so hopefully this session is you can understand and beneficial to you. All right. So next class we're going to continue with elementary flows. So we end our class with class B Kifara and Sarawak. Okay, puasa rajin-rajin, beramal dengan yang baik mungkin. And Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, sir.